80% of wastewater that's generated around the world isn't collected. It just goes out into the environment, often without treatment. And so we're talking billions of liters of wastewater being discharged to the environment. It's a threat for pollution, of course, and it's a lost opportunity.
Will Tarpeh, Assistant Professor of Chemical Engineering at Stanford University, is focused on harnessing that lost opportunity with wastewater through chemistry. It's what landed him on the Chemical and Engineering News' 2019 Talented 12, a list of brilliant young scientists taking on some of the world's toughest problems with clever chemistry. And it's also how he came to be one of the most prominent young scientists on the chemical scene, being named one of the 100 most influential African Americans by The Root and appearing in Forbes 30 Under 30 in the science category. In this sixth and final episode of the Science with a Twist series, Bringing Chemistry to Life, we speak with one last member of the Talented 12 about their work and trends in their field. I'm your host, Paolo Braiuca, Senior Manager of Global Market Development at Thermo Fisher Scientific. We began by asking Dr. Tarpeh about his background and what took him to his current role.
I was born in West Africa, and my dad is Liberian, my mom is Black American. And so I grew up kind of between the west coast of Africa and the east coast of the US. I found myself as a child really fascinated by science and always by the environment. So I was always really interested in how things worked around me, being in nature and thinking about it. I also thought a lot about how science could impact people's lives in terms of improving people's lives. That got me really interested eventually in water, but kind of meandering through all different types of science. As a kid, I was really interested in paleontology. I loved doing fossil digs that I would hide fossils for myself and then find them a couple of weeks later. That was like really exciting to me, that element of discovery when I look back at it. But I got interested really in water, kind of in middle school, high school, and then even more interested in wastewater. Drinking water we view as very clean, very aspirational. Wastewater we view as the exact opposite in so many ways, but they're often connected in this cycle that we don't always acknowledge. We might install a well or think about ways to clean up drinking water, but we don't think about the fact all the time that wastewater often becomes someone else's drinking water. What people treat as trash and discharge, there's value in it, and what if we could recover it? And that's really the backdrop for everything we do in my lab, is the quote we often think of is one person's trash is another person's treasure, and we're the second person, so that's how we think about it.
What is the main driver here? Is it your interest for nature, your interest in people, your interest in making a difference? Because you could potentially tackle an area that was not particularly looked after.
The drivers are twofold. One is I love really interesting science. I love a good scientific challenge and pulling the needle out of the haystack from a chemical perspective. So that's always driven me. And then I was always driven by really tangibly improving someone's life. So when I did internships in college, the ones were most excited about were the ones where I could meet the people who were the motivation for my work, right? So like doing work in sanitation, I could meet people who benefited from toilet installations and things like that. That was really gratifying for me and helped drive the discovery and the scientific part, because I could think of, early on it was like I could think of that person, right? But now it's easy for me to just say, I can think of this group of people who I think would benefit from these innovations. So I love doing fundamental science, but with the application like really already in mind.
I think this is a recurrent theme, and there's always this sort of correlation between the love for science and the problem-solving aspect that most scientists have, but also with this drive and desire to make it real, right? To ensure that you impact life. And what is wastewater really? How much of it we have, and what there is in it that is valuable?
When I think about the definition of wastewater, in most cases, any industry, any installation that has a physical pipe that takes some liquid stream and discharges it to the environment. Once it crosses the physical boundary of that installation, I'm interested. It's the wastewater part. And so that broadens the definition, because most of the time when I say wastewater, the picture that pops into people's minds is a wastewater treatment plant. I love to broaden that definition because there are many different types of wastewaters. They're all different. They have different compositions, and thus they have different value because they have different components. So wineries have wastewater. Any chemical industry you can think of has wastewater, but so does agriculture, right? There are so many things that generate wastewater. So it's water that goes out into the environment And in terms of how much there is, 80% of wastewater that's generated around the world isn't collected, right? So it just goes out into the environment, often without treatment. And this is worldwide. And so we're talking billions of liters of wastewater being discharged to the environment. It's a threat for pollution, of course, and it's a lost opportunity, a series of lost opportunities, because we put all this money into generating these valuable chemicals, and then we discharge some portion of them, a large portion of them, into the environment.
So spending energy and money to generate value and then discharging a lot of this value into the environment and forgetting about it and then keeping spending money to regenerate it.
That's not a bad thing. I don't mean to demonize it. I just think in the 20th century, we weren't as aware of pollution as we are now. We weren't as aware of the costs of the linear economy, nor were we as aware of the opportunities of a circular economy. Now we know we're putting money in and we're leaving money on the table.
If I think about all the different wastewater definitions that you just described me, what are you really focusing on? Are you really looking at all of them?
We definitely cut off a bite-sized piece of that we're most interested in. But definitely the big vision, I hope that in 20 to 30 years, people ask me what wastewater is. And it's like, that term is obsolete because it doesn't exist, because there's no such thing as wastewater. That's kind of the vision I work toward. In the same way, inspired by biology, right? So like, ecosystems don't have the same concept of waste, right? One organism's waste is another organism's input. That type of circularity is what I would love to see and what me and my group work towards in terms of the chemical industry. But in terms of the compositions of these different wastewaters, the few pieces that we take on, one that's really captured our imagination is the nitrogen cycle, inorganic nitrogen in particular. There's so many different forms of nitrogen. They have different oxidation states. We can convert them between each other. Nitrogen is so captivating to us because it's one of the cycles that humans have changed the most. So we have all this reactive nitrogen that we're pumping into the environment with very little removal of it. And so we take that a step further and say, let's not just remove it, because that would take two energy intensive processes, right? Haber-Bosch and then conventional nitrogen removal. Let's recover it. Let's keep it as reactive nitrogen. We've already done the work of reducing it to ammonium. Let's keep it that way. And so that's something that has captured our imagination. Part of me keeps trying to get away from it and diversify, but I just keep getting pulled back into it. So now we're thinking about nitrate, ammonium. What about gaseous nitrogen, right? NOx emissions and N2O emissions. How many of these can we turn into valuable products? So that's one big area of the work. Another area we've got really interested in is desalination. And there's lots of work going on desalination, turning seawater or wastewater or brackish water into potable water. Our perspective on that is that even desalination generates wastewater. So if you take ocean water, you'll make less salty water that's potable. You will also make a volume of saltier water. And that brine is something that we still can get value from. And so that's what we're after. So even in kind of green technologies, we're still after squeezing all the value out.
Is the vision tackling one by one these different types of chemistry in a different type of wastewater? And overall, the vision, long-term vision, is that we will have circular economies for all the wastes.
I tend to view circular economies as actually element specific. So we talk about a circular nitrogen economy, but there should also be a circular phosphorus economy. I view these as loops of each element that you can look at. And then we ask questions like, how many times can one molecule of nitrogen go through our industrial ecology? And how much value can we get to, like 7th generation nitrogen, right? So maybe you've seen like 7th generation dishwasher liquid. Can we get 7th generation nitrogen? What would that look like?
And that makes a lot of sense to me, because I imagine the chemistry for each element is going to be fundamentally different. So you actually need to tackle the different circles with different kinds of approaches. So they have to be looked in isolation.
Absolutely. Right. So when we think about the separations that we design, whether they're electrochemical or adsorbent based, the different characteristics we exploit to get just nitrogen out. They might be things like hydrated ionic radius or electronegativity, these sorts of things, to get nitrogen away from potassium or sodium. There's a different logic if we want to think about lithium. Lithium is another thing we've started thinking about. Lithium has a whole different mechanism of selectivity, so to speak. Its hydrated radius is really different from sodium, ammonium, and potassium. So we call these sort of like resource recovery cases, and it's kind of a three-part thing that we think about. It's like, what's your target wastewater? What's the wastewater where this nitrogen or whatever element you're after is present in high concentrations? Then there's the target element. What element are you after? And then there's the target product. Are you trying to make a fertilizer? Are you trying to make a disinfectant? So with those three things, we sort of juggle those around to make each resource recovery case that motivates a line of our research.
But I assume that wastewater are more complicated than that. You don't only have nitrogen pollutants in it or phosphate pollutants, you've got a mix of those things. So is the vision sort of combining all these different cycles somehow by a sort of pre-processing of the original water stream, dividing it in separate wastewater types that can be treated separately chemically or physically?
To your question of different wastewaters having different compositions, absolutely, because we absolutely think about that and leverage that because it does some of the separations work for us. So as an example, another thing that we continue to do, and I really just own now, so my C&EN moniker is the Waste Wizard. And so this is a thing my group has really owned, so I dress up for it. This will be my second Halloween dressing up as a waste wizard. But part of that is because one of the things that has captured our imagination a lot is urine, human urine. And so sometimes people who I meet are like, oh, you're the urine guy. And I'm like, okay, that's one thing I go by, not the chief thing, but it's one thing I go by. And that's because urine is one of these cases. Urine is 1% of the wastewater volume that's generated, municipal wastewater, but it has 80% of the nitrogen in it. So it's done the work for us, right? Our bodies have done the work for us in terms of if we want nitrogen from municipal wastewater, getting it from urine is 100 times easier than getting it from municipal combined wastewater because it gets diluted 100-fold. And so that's why we go after urine, because the separation, it's like the pre-treatment you mentioned. There's a pre-treatment there. Urine is high in nitrogen. It's going to be an easier separation. Let's go for that.
It's a perfect model system for you guys. And okay, why is nitrogen considered a pollutant? You mentioned the fact that humans actually affected the homeostasis of the natural environment, just skewing the equilibrium. And I believe that nature just can't cope with that. So there's no mechanism to go back to a perfect equilibrium like when humans didn't have the Haber-Bosch and they were making so many fertilizers and explosives. Is it that? And what does this imbalance causes to the environment?
The major forms of nitrogen that cause pollution in water are